So today we are doing experiment 6, thermodynamics, and I am doing part 1 of the procedure, or really it's a modified version of the procedure, and I'm going to do it multiple times with different containers so that we can compare the containers. So in part 1, we are determining the heat capacity of the calorimeter. Put in more simple terms, we want to know how much of the heat from the solution is being lost to the cup or the container it's in. And so this is my basic setup, and I'll zoom in on each of these. To the left side, we have our calorimeters, the containers, and behind those I have a magnetic stirring stand. I have some room temperature water, and I have some water that is being heated up. And according to the procedure, it should be about 70 degrees Celsius. The exact temperature is not important. We will record it when it's time, but it just should be something in that range, something pretty hot. Here is a close-up of the 4 calorimeters that I'm going to use. So on the far left, we have this one, and it's pretty old. This is made out of aluminum, and it has a wood lid. This one's probably been in the classroom or previous classrooms for 30 or 40 or maybe 50 years. Some of our stuff is up to 60 years old. So with this one, basically it has a wooden lid with 2 holes, one for the stirring rod and one for the thermometer. And it just goes on like that. So let's move the lid out of the way. Now, each of these containers is really 2 containers combined. And you can see with this one, I have a smaller aluminum cup inside of a larger one, and they're separated with this hard plastic ring. And the purpose of this is so the containers don't touch and they won't conduct the heat back and forth. And it creates a layer of air on the inside, and air is a very good insulator. And so this is one type. The issue we have with these, it's not compatible with our magnetic stirring stand, which you can see back here. It has a little magnet, and when you turn it on, it spins. And it just eliminates a lot of work for us because we don't have to constantly stir it. With this older one, it has a stirring rod that comes with it, and you basically have to move it up and down the entire time, like you're churning butter. So I'll just leave that off. The second type is the one that you typically encounter in chemistry classrooms and in lab procedures. And this is 2 styrofoam coffee cups, and each one of them is pretty good at insulating and not letting heat escape. If you've ever had hot chocolate or coffee in one of these, which I'm sure all of you have, you can feel the heat through the walls of the container, and that is the heat of the solution leaving through the container. And that's what we're testing. But really, in order to make this work well, we put 2 stacked together, and it leaves this small layer of air in between them. And air is excellent insulator. And so this is one that really it works pretty well, and it's not too expensive for our lab. This next one is a cheaper coffee travel mug, and these are also double walled. So on the outside you have this aluminum layer, and on the inside this one's plastic. And really these work pretty well for what they're worth. This also has a lid, and it doesn't have a hole necessarily for a thermometer, but it does have a hole where you can drink through it. And then the final one, this is a more substantial coffee travel mug, and it's also double layered. Both layers of this one are aluminum, and we're going to see which one of these 2 would work the best. So you can compare your travel mugs this way. If you had something expensive like a Yeti, we might expect it to do better than these, but who knows, maybe we'll test it. Now, normally for a calorimeter and for your part 1, you will have a lid for the container. Now, the lid just makes sure that we're not losing heat at the top of the solution. But I have different lids here, and really all of them have about the same size surface area where the solution comes in contact with the air. And so I'm going to do this experiment without the lid, just so I don't have to drill holes in my coffee lids, and it'll kind of make it a constant. So I'm going to go through each one of these with the first procedure, part 1. Okay, so here are my 2 samples of water. On the left, you can see 3 wash bottles, and I'm going to use 50 milliliters of this water. It's at room temperature. I filled these bottles up about 24 hours ago, and so they are the same temperature as the room. All of this water should be the same temperature. Just to be thorough, I will take its temperature every time before I start a new experiment, but it should all be about the same temperature. On the right, you can see I have a hot plate with some water, and this has been heating up for not too long. It's approximately 80 degrees Celsius, so it's a little warmer than the procedure indicates, but it'll be okay. It just needs to be hot water, and I'm going to take its temperature immediately before we combine these. You might notice that I have 2 thermometers in here. Yesterday I went through and I calibrated all of my thermometers. These were my 2 best thermometers, and they still have a little bit of error. And so I'm going to use both of them, and I'm going to average out the temperature between the 2 thermometers for every piece of data. When you do this experiment, 1 thermometer is fine. I just wanted to see how these 2 thermometers work in relation to each other. So you'll also notice that down here I have 2 instruments, and these are just so that I can handle the beaker. 80 degrees Celsius is awfully hot to be touching with your bare hands, and so I have 2. This is kind of like an oven mitt and some tongs. I'm also going to be using a 100 milliliter graduated cylinder for the hot water, just because I want that extra long stem so that I can have a handle without having to touch the hot water or the hot glass. Here we are looking at our first calorimeter, and you see I have both my thermometers set up, and it's on the magnetic stirring bar. Something to keep in mind is that when you are setting this up, you want to make sure that your thermometer clamp isn't blocking the temperature range that you want to read. For instance, 20 is here, that's my room temperature water approximately, and my hot water is approximately 80. And so I don't want this clamp to be anywhere in the 20 to 80 range, because it's going to end up messing up my data. I'm going to miss several temperatures, and so we need to make sure that they're both clear. So I'm looking down on the calorimeter now, and I'm using a magnetic stir bar for all of these, but this calorimeter is just not working with the magnetic stir bar. Now, it's metal, yes, but it's aluminum. So the aluminum's not messing with the magnetism. The problem that we're having is that this magnetic stir bar is about 3 inches above the plate that it's supposed to be resting on. And so it's just a little bit too far outside of that range for the magnet to really work. Another thing about these thermometers, we want to make sure that the bottom of the thermometer, where it reads, is not actually touching the inside of the container. You want it to be only touching the liquid. At this point, I have everything set up. I've taken the temperature of the hot water just a second ago. I have both thermometers situated in the calorimeter, and I have recorded the temperature of the cold water. Now, before I mix them, some last things to double check. One, do you have your data table ready with a pencil? We need to be able to write things down as soon as we start. Secondly, we have to run a stopwatch. We're recording the temperature every 20 seconds, and so the moment you mix it, you'll want to start the clock. This is where it helps to have a lab partner. I'm just going to be as quick as I can. I'm going to pour it off, mix them, start the clock, and then I will start reading temperatures. Just want to make sure that everything is in order before you start this because it is time sensitive. Okay, so I just finished my experiment testing the specific heat of this particular calorimeter, the aluminum one. Now with the aluminum one, like I said, the magnetic stir bar wasn't working because of the height, so I had to use a glass stir rod, and I was also taking the temperature every 20 seconds. So this one's done. I didn't want to make you sit there and watch me take temperatures for 3 minutes. I'm going to go ahead and set up everything else for the next one, and then I will just give you a little piece of what the setup looks like, and then we'll go into talking about what the data looks like. So next up, I'm using the 2 styrofoam coffee cups to run this experiment, and I've already measured the hot water temperature on the hot plate just a second ago, and I just recorded the cold temperatures here. And right before I start, I want to show you one thing. I mentioned not having the thermometers touch the container, but you also want to make sure that your thermometer is not going to come in contact with your stirring bar. And so I'm doing a little dry run here, and it looks like it's just out of the way. It creates quite a disturbance, so you don't want to have it on for too long before you mix them. What I'm going to do is mix them, start the clock, and then I'm going to turn this on to minimize any splashing or other factors that may occur. One other thing to note before I start this is that I did have to resituate my thermometers and my thermometer clamps to get them in the right positioning. You want to make sure that your thermometer probe is completely submerged, but also not touching that container. So I'm about to start my third trial, and this one is with it's a travel mug. It's a cheap one. It's aluminum on the outside and it's plastic on the inside. I've never used it for coffee, but it doesn't seem like the kind of travel mug that would keep coffee hot for a long period of time. I've modified this experiment a little bit. Now that I've done 2 trials, I know how the thermometers are related, and so I'm only going to use one thermometer from here on out. I'm going to go ahead and take my room temperature water and put it in here. And I want to show you the problem I have with using a coffee travel mug for a calorimeter. So let me zoom in so you can see this. Okay, so here's the issue I have. I've got my hand here so that the camera stays in focus. I have this thermometer about 1 millimeter off the bottom of the container. It's important they don't touch, but that's about the closest I can get. It's just barely off at the bottom. Here's the thing about it. The 20-degree marker is basically inside of the container. And so the issue we have is that if we started with water any colder than this, then my reading would be inside the container. And if I put a lid on this, you would not be able to see the 20 marker. You wouldn't be able to see anything below 25 or 30. And so it could disrupt our data. And so I'm going to go ahead and run this experiment, but just based on this, we might not want to use this in a regular everyday experiment. Okay, so this is my second travel mug, and this one seems a little more substantial. It's double walled, both sides are metal. It seems like it would be a nicer one. Here's the problem I'm seeing with the experiment. If you look here, I can't see anything below 35 degrees Fahrenheit, and I have the room temperature water in here. And in order for me to measure the temperature, I have to be looking down on it, and it's kind of messing up my reading. And so this is not ideal. What I'm going to do is pull this out very quickly, and it looks like 21 point, let's say 1, and then I'll put it back in there. So this is not a great experiment already. If we were going to do multiple experiments with this container, we would want to have some different style thermometer, maybe the electronic kind with a wire probe that sticks in. So I'm going to go ahead and run this experiment, and I will show you all of the data at the end. Okay, because of the challenges of trying to get the temperatures recorded with this experiment, I'm going to set the camera on it, but everything from the 20 degrees Celsius mark to about the 40 degrees Celsius mark is obscured by the container itself, and we're looking down on it, which means we're not getting an accurate reading. And so we're going to run this one, and I'm going to try to take the temperatures, but I'm going to mark it with an asterisk that says that our data was highly prone to error because we didn't have a clear view of the thermometer. Okay, so the black coffee container had so many difficulties that I'm just going to toss out the data. In fact, I didn't really get any good data. But what I'm going to do now is add on something I wasn't originally planning on. I'm going to use a single coffee cup. Remember, our coffee cup calorimeter was 2 coffee cups stacked for extra insulation, styrofoam, air, and then styrofoam. And so in this one, I'm going to show you how that compares with just a single walled styrofoam container, and we can take a look at the differences there. So this is my data analysis for experiment 6, part 1, where I check the calorimeter. Now, real quick, some brief differences. You're only going to test one of these, probably the double-walled styrofoam, and you're also going to have a lid on it, and you're going to run it at least 3 times. I only ran this once because I used a bunch of different calorimeters. Let's look at the calculations here, and I'm going to run through these pretty quick. If you need to, pause the tape, and you can write down as I go. Some important numbers. There's one we call T-mix. This is something we extrapolate from the graph, which I'll show you here in a minute. Then we have T-average. This is you take the temperature, the hot temperature and the cold temperature of your 2 original samples, divide them by 2. That'll give you the exact average. And then how are we going to calculate delta T? This is the final temperature of the experiment, which is at time 180, minus the T mix, which is the number that we get from the graph. We want to know the Q cal, which is the heat of the calorimeter, and it is opposite in sign, but equal to the Q for water. The Q for water is what we're really measuring here. We know how much water there is, we know the specific heat of water, and we know how much the temperature of the water changed. So we're going to use our data for the water, flip the sign to figure out the amount of heat absorbed by the calorimeter. Then we are going to find the specific heat of the calorimeter. This is C cal. We're going to use the heat absorbed by the calorimeter, which we just found. And we're going to divide that by the T mix, remember from the graph, minus the initial temperature of the cold water. So I'm going to show you my data for each and every one of these, and you can see how everything worked out. So this is for the original aluminum calorimeter that you saw, and I put this in Google Sheets pretty quickly. You can see my time data and temperature data, and here I have a scatter plot with the best fit line. my initial hot temperature, my initial cold temperature, those are at the top. They're not in my data table because I didn't want them to show up in the graph and throw off the best fit line. So T mix, this is the one that comes from the graph. So I've got this graph and the data goes from here to here. And this best fit line, if I trace it back, lands here. And this is your T mix. That's how you're going to find this temperature. The average temperature was the temperature of the hot and the temperature of the cold, add them together, divide by 0. Delta T is, remember, this temperature, the final, minus the T mix that we get from the graph. We use this delta T, it goes into our Q formula, MC delta T. Remember, we're calculating this for water. Now the mass of the water. I know the volume, it was 100 milliliters. And I know the density they told us to use, 1.02 grams per milliliter. And so these are the numbers that I have. The water lost 767 joules, which means the calorimeter absorbed 767 joules. Put that into our C-cal formula. Here's Q-cal. This is my temperature at this is the T mix temperature, which comes from here. This is the initial cold temperature, 19.8. And all of that will give you a number. And these two things are really what you're interested in. Most of all, this one, because when you get to parts 2 and beyond in this lab, you have to know how much heat is your calorimeter going to absorb. So what this is telling me is that for every 1 degree Celsius change in temperature, the calorimeter is going to absorb 40.4 joules of heat. And so we are losing energy to the calorimeter, and here we have a nice rate to show us what's going on. One last thing about the aluminum. When I first began the experiment, the aluminum felt pretty cold because it's got a very low specific heat and it absorbs a lot of energy pretty quickly. When I disassembled it, the inner container was really pretty warm, the same temperature as this. And so I think initially, let me erase this so we can get a good look at it. If you were to follow the data along, it actually starts here and then levels out. And so I think what happened is probably the original temperatures together were here, but there was such a shock to the system and it was being absorbed by the aluminum that it probably went like that. But that's not something we can represent because that's purely speculation. That's not actually in the data because we don't have that initial mix temperature. Here's the double-walled styrofoam container. You see I have all the calculations here, and we find out that the C calorimeter is 35.2 joules per degree Celsius. And these ones are following a pretty decent line too. Here's the blue travel mug, and you can see that the calorimeter absorbed 53.5 joules per degree Celsius. And if you compare that to the double-walled styrofoam, the styrofoam actually did better. And here, since the black travel mug didn't work, I couldn't read the temperatures accurately because of how tall it was. I went ahead and did a single-walled styrofoam just for comparison. And the initial temperatures are approximately the same. But look at this, the delta T was quite a bit smaller. If we Look here, delta T for the double wall was negative 1.7. Delta T for the single wall is negative 0.8. And what this says is that the calorimeter actually absorbed less heat here, and the C for the calorimeter, according to my calculations, is 16.7 joules per degree Celsius, which would indicate just by the numbers that this one might be the best out of all of them. However, we have to factor in a few things. We only went to time equals 180. It's possible that after 180 seconds, if we're talking about going all the way to maybe 10 minutes, then we might see a divergence later on. We might see one doing better than another. According to the data, this blue travel mug is the worst. The double-walled container is okay, and the aluminum was not bad either. Now, like I said, when you do part one, you're going to do this experiment with the same calorimeter 3 times, because we really want to know how well is yours doing. The data in one trial could be a fluke. Is this one really the best? I don't know. I only did one trial. If I were really curious to know is the single or the double walled better, I would go back and do each of these 3 times, maybe 5, maybe 10. And so we need to know how well is this thing going to do. Further experiments would be necessary. That's it for the part one. Hopefully this is helpful. When we come back, you're going to do this yourself, and it's going to be, like I said, 3 separate trials at least.